Everyone to a brief video on correlation and how to interpret correlation coefficients. We have been going through regression, and hopefully in reading up the content for this topic, you've come across the word correlation. I hope that a lot of the confusion around the word correlation and relationship is sorted now. The two are not interchangeable. They are not the same thing. Correlation is a statistic that we use to measure the strength of a relationship. It's a statistic like a mean, like a standard deviation. Okay, it's just a statistic that we use to measure a certain aspect of data. In this particular context, when you're looking at two different variables, correlation coefficients will tell you whether they have a relationship and how strong that relationship is, and the nature of the relationship. So I use the example that we had in class where we were looking at the relationship between shoe length and a person's height. We were trying to use shoe length as our X variable, our predictor, for our target variable, which was height. So as long as we have somebody's shoe length, we should be able to predict their height. And this was the scatter plot we came up with. On our chart, we actually have the capacity to add correlation to a chart. So I'm just going to click inside this chart so the chart editor comes up. The same place where we added our trend line, the series menu, okay, of the customize tab. If we click on the series menu, you'll see that we added our trend line by clicking the checkbox right to the end of this menu. There's another checkbox called show R squared. R squared is variation for correlation. If you click it, you'll see I now have an R squared value at the top there. And R squared value that I got was 0.307, so that is the measure of correlation for this data. To your graph, and it's always good to have both your trend line and showing up on your graph. The markers of a good graph are a good title, good axis labels, units, and R squared included. R squared also comes as a unit of your written from Excel Miner or from the data analysis toolpack. I've highlighted here in purple. So at the top of your summary output, you get a few statistics around regression. Remember, observations is the number of observations in your sample, so it's a sample size. And I said to you guys that because we've got 10 people, this is a sample size of 10. It's not a sample size of 20 because we have 20 numbers. Okay, it's a sample size of 10 because we have 10 people who we collected two numbers from. We collected their shoe length and we collected their height. So each pair of numbers is with observation. So there's 10 observations in this data set. This is the standard error. It's like the standard deviation. Okay, it's a standard error of our combined variables. And then we've got multiple R squared and adjusted R squared, and all of these are measures of correlation. The ones we tend to talk about more are R squared and adjusted R squared. We use R squared when we're talking about simple linear regression. When we've got multiple linear regression, we use the adjusted R squared. But both of them give an indication of the strength of the relationship. Okay, and you'll notice that we were doing a simple linear regression. We only had one X variable. So this wasn't a multiple, it was a simple linear regression. The R squared value that we got is the same as the value on the graph, which is what we want. Now, in terms of how we interpret R squared, this is essentially, this color-coded line is essentially a number line, okay? If you think about this color-coded line as a number line from -1 to 1, it crosses 0 in the center. This is all the value that R squared can take. So R squared can be any number between -1 and +1. You will never get an R squared of 1.7 or an R squared of 22. It doesn't happen. Okay, that's beyond the scope of what R squared can tell you. So R squared stays between -1 and 1. When you have an R squared of 0, okay, of exactly 0.000000, that is called no relationship. Okay, when you have an R squared of any number other than 0, then you have a relationship, and you can interpret whether that relationship is negative or positive. You can also interpret whether that relationship is weak or it's strong. It's rare to get an R squared of exactly 0. Okay, but it does happen. It's been known to happen. It's just very rare. So normally you'll get an R value somewhere between 0 and 1, or somewhere between -1. If your R squared is on the positive side, then your relationship is a positive relationship. You'll see that we have a positive number here. So, and our line is also, which is a positive gradient. Because we have a positive gradient and a positive number on our R squared, we can say the relationship between shoe length and height is positive. The higher your foot, the taller you are. Okay, so as I increase on these numbers, I increase on these numbers as well, which is why it's positive. If this line was tending downwards, if as I was going here, I was on my y-axis relationship, it is possible. It doesn't mean the relationship is bad. It just means that's the direct relationship. Sometimes you want an increase in something to cause a decrease in something else, and that would be your successful outcome. Okay, so here we have a positive relationship. Now, when you've identified whether your relationship is negative or positive, you can go further to see, is my relationship strong or weak? Okay, on both sides. Now, what defines a weak relationship is a number that is close to 0. The closer to 1 you are, the stronger your relationship. The closer to 0, the weaker your relationship. So from 0 to 0.5, you have a weak relationship. From 0.5 to 1, you have a strong relationship. A number like 0.3 is closer to 0, so it's on the weak side. Okay, so our 0.307 is a weak positive relationship. Okay, and the same can be said for the other side. If you had a negative R squared, you can also see if it's strong or weak by checking whether you're closer to 0 or you're closer to -1. A strong relationship would be between -0.5 minus. If and that's how you interpret your R squared. That interpretation essentially makes up the inference for your graph. So something you didn't get to do was to write an inference of what we see on our graph. Every time we do a visualization, you have to write what you are seeing. Okay, you have to interpret it for your audience. So I did it already here. I'm just going to bring it over. Okay, and our inference is based on what we see, but it's also based on what we put on our plot. We've got a measure of R squared, so this is a chance to talk about what your correlation coefficient is and what it means. So you'll see here I've said based on the wide scatter of points in the graph, shoe length appears to have a weak relationship with height. This is something we spoke about in the lesson. We agreed that this wide scatter here, okay, isn't great. For this to be a great relationship, our points would have to all be lying more or less on the line, okay? The wider the scatter, the weaker the relationship. So this is what our R squared confirmed for us. And so I'll go on to say, since the R squared is 0.307, the relationship can be considered to be a weak positive one. And that's what we spoke about earlier. Another thing you can say from R squared is you can convert this number to a percentage. And R squared will actually tell you how much of the variation in your target variable is due to the variation in your explanatory variable. So how much of what we are trying to predict can be said to be dependent on what we think is explaining it. Okay. If I convert that number to a percentage, 30.7% of the variation in height is due to the variation in shoe length. These two interpretations are both very important, okay? They're not the same thing, so you do have to say both of them, all right? And this would be essentially the inference of a scatter plot. This is how you describe what you are seeing. And that's it. That's how we interpret correlation. I will show you a couple of our slides, our class slides that we didn't get to talk about, and I'll just show you different plots where you can see and almost guess what the correlation in that instance would be. And I will post these slides, and I'll post the example on Catch the Thief. I'll post them on our platform so that you have access to the video and the written work. Now, since we've spoken about correlation, if you take a look at the scatter plots here, you can actually essentially have an idea of whether that correlation is, or the relationship is a good one, if it's a positive one, if it's a negative one, but also if it's a strong one based on the scatter plots. So at the graphs below, here I was plotting different variables against D grades and trying to see which variables seem to explain in our grades best. So in the first graph, study time and does it, when you look at study time and scores, that the more you study, the higher you score in your tests. So I've got DD grades compared to study in hours, and because my weekly study is what I'm using to explain grades, my weekly study is my X variable. My grades are the target variable, so they will have my trend lines, and I've done that on purpose just so you can imagine what. If you have a trend line here, it would probably be positive. We have a lot of data, which is great. When you have 10 observations like we had before, you saw how that's not a great start time. It's difficult to see what's happening. So if I was to add a trend line, it would probably be positive, but there is quite a bit of scattering. But it's safe to say there is some kind of a relationship, a positive relationship between the amount of time you study and the grades you get. Based on this, I would say maybe on the weak side, but we would have to then calculate R squared to confirm whether it's a weak or a strong relationship. Here, what I compared in the next graph is leisure time, okay? And what I wanted to see is whether too much leisure doesn't help your DD grades. So I've compared DD grades to the hours you spend in leisure, and what expected to see that the more time you spend playing, the less your grades. Okay, so you are likely to fail if you are playing for 16 hours a week. And it looks like that's a general trend. This time I have a negative relationship, which is what I expected to see. My scatter points tend downwards. I would expect my trend to tend downwards. But again, there's a lot of scatter here, so I would say possibly a weak relationship And you can go and create these graphs on your own as well to see what you come up with once you put in the trend lines and once you put in the R-squared values. And here on the left, I've got DD grades compared to self-work. And in terms of self-work, I was measuring your attempts in self-work by the number of correct answers you got in your self-work. And this seems to be my best relationship so far. My points are much closer together than in the previous two graphs. They tend upwards, which means this is a positive relationship. So the more questions I answer correctly in my self-work, the higher my grades. This seems to be a really good indicator of what your DD grades would be, better than how long you study. Okay? And then I threw in a complete variable. On the right, I compared the amount of time you spend on studying EL to the grades you get for D&D, which, as you can see, it doesn't even look like there's a positive or a negative trend to this data. The points are just more or less in a straight line. Okay, so there's almost no relationship between these two variables. Again, you can put a trend line and calculate your R-squareds to check those values and verify what the actual numbers say. But now you've got an idea of what your points look like and what they indicate and what to expect once you put your trend line and calculate your R-squared value. I hope that's been a useful exercise. Like I said, I'm going to post the slides and the worksheet, the Google Sheet that we used, including this video on our Google Classroom platform. All the best with your assignments. See you all on Monday.